Imagine a place far, far away, in the deepest, darkest corners of the universe, billions of light years from home. Here, two giants of the cosmos, two massive black holes, are locked in a final, deadly dance. Each one is a monster of gravity, so dense that not even light can escape its grasp. For eons they've circled each other, pulled closer by the invisible force that governs the stars. Their cosmic waltz accelerates, spiraling inward faster and faster, a prelude to one of the most violent events the universe can muster. As they draw closer, they begin to warp the very fabric of existence around them, creating a cosmic symphony of destruction and creation. They are now on a collision course, a point of no return. In the final fraction of a second, they merge. The collision is silent, yet it is a cataclysm of unimaginable power. This isn't an explosion of light or matter, but an explosion of space-time itself. The two singularities become one, forging a new, even larger black hole. In that single, violent moment, an amount of energy equivalent to many times the mass of our sun is converted not into light, but into pure gravitational energy. This energy erupts outwards, not as a flash, but as a tremor, a ripple that begins to travel across the cosmos at the speed of light. These are gravitational waves. They are not waves traveling through space. They are waves of space. Picture dropping a stone into a still pond. The ripples spread out, distorting the surface of the water. Now, imagine that the pond is the entire universe, the four-dimensional fabric of space-time. The merger of the black holes is the stone, and the ripples are gravitational waves. As they propagate across the universe, they stretch and squeeze everything in their path. The distance between 2 points rhythmically expands and contracts as the wave passes through. It's a cosmic storm, but one that is completely invisible to our eyes. For billions of years, these waves travel, their journey uninterrupted across the vast emptiness between galaxies. They pass through nebulae, star clusters, and entire galactic arms, their energy slowly diminishing over the immense distance. Their origin story, the violent embrace of two black holes, is encoded in the shape and frequency of the wave. They are like cosmic messengers, carrying a story from a time long before our planet even existed, from a place so distant it's almost beyond comprehension. They carry the secrets of gravity in its most extreme form, a pure test of Einstein's century-old predictions. Finally, after a journey spanning more than 1 billion years, these ripples reach our cosmic neighborhood. They sweep past Jupiter, Mars, and finally, they wash over Earth. At this very moment, a gravitational wave from a distant cosmic collision could be passing right through you. You wouldn't feel a thing. The effect is impossibly small. As the wave passes, it stretches and squeezes the space you're in. For a fleeting instant, you are infinitesimally taller and thinner, then shorter and wider. The change is smaller than the width of an atomic nucleus. The room you're in, the planet itself, is being gently squeezed and stretched by this echo of a cosmic cataclysm. But it's not just space that's affected. Einstein taught us that space and time are intrinsically linked into a single fabric, space-time. So, as a gravitational wave distorts space, it also distorts time. The renowned physicist Kip Thorne, one of the pioneers of gravitational wave detection, described it as a storm in time. As the wave passes, the rate at which time flows speeds up and slows down in a rhythmic pattern. Your clock, for an infinitesimal fraction of a second, ticks ever so slightly faster, then slower. It's a mind-bending concept. Time itself is not constant, but is being subtly altered by an event that happened 1 billion years ago, 1 billion light years away. So, if these waves are so faint, so imperceptibly small, how on earth could we ever hope to detect them? The answer lies in one of the most sensitive scientific instruments ever built, the Laser Interferometer Gravitational Wave Observatory, or LIGO. There are 2 LIGO detectors in the United States, thousands of kilometers apart. Each one is a giant L-shaped instrument with 2 arms, each 4 kilometers long. Inside these arms, a powerful laser beam is split in 2. One beam travels down one arm, the other down the second. At the end of each arm is a perfectly polished mirror. The laser beams bounce off these mirrors and travel back to the point where they were split. Here, they are recombined. Now, if the 2 arms are exactly the same length, the light waves should recombine in a specific way, canceling each other out so that no light reaches the detector. It's a state of perfect balance. But if a gravitational wave passes through, it will stretch one arm while simultaneously squeezing the other. This tiny, tiny change in the length of the arms, less than 1/10,000th the diameter of a proton, is just enough to knock the laser beams out of perfect alignment. When the returning beams are recombined, they are no longer perfectly out of sync. A tiny amount of light leaks through to the detector, creating a signal. This signal is the sound of the gravitational wave. By comparing the signals from the two widely separated LIGO detectors, scientists can confirm that the signal is real and not just local noise, like a passing truck or a tiny earthquake. They can then triangulate the wave's origin in the sky. On September 14, 2015, for the first time in history, both LIGO detectors registered a clear, unambiguous signal, a chirp, that perfectly matched the predicted sound of two black holes merging. That discovery was a monumental achievement, opening a brand new window to the universe. For all of human history, we have studied the cosmos using light. Visible light, radio waves, X-rays, and so on. But gravitational waves are different. They are not light. They are vibrations in the fabric of space-time itself. This means we can now hear the universe's most violent and hidden events. We can listen to the collisions of black holes and neutron stars, events that are often shrouded in darkness and invisible to our telescopes. It's like gaining a whole new sense. We've been watching the cosmic movie without sound, and now, someone has finally turned on the audio. This new era of gravitational wave astronomy is just beginning. With every new detection, we learn more about black holes, the life and death of stars, and the fundamental nature of gravity. We are probing the moments just after the Big Bang and testing the limits of Einstein's theory of general relativity. We are piecing together a more complete picture of our universe, one that includes its hidden, gravitational symphony. It all started with two distant giants in a final cosmic embrace, sending a message across space and time. A message we are finally able to hear. Thank you so much for joining me on this journey through space and time. If you found this as awe-inspiring as I do, please hit that like button and consider subscribing for more deep dives into the mysteries of our universe. We'll see you in the next one.